Okay. The delay is like 10 seconds. But it's working. So if you have questions, you can type it in the chat, or I'm going to be singing the IEEE Discord in a voice room, so you can just verbally ask them there as well. Okay, I mean it's not 6, but I'll start now. So this is the IEEE ENA test review for Dr. Chiu's class, right? And what I plan on talking about, or what I plan on covering on your test. So, from what I understand, your test covers like you have basic circuit elements, so that's like resistors, all that basic background knowledge, and then you'll talk about resistor networks, and this is where you talk about KCL, KVL, etc. And then the big topics would be node voltage, mesh current, Thevenin / Norton, and I think these are your big topics, right? As far as a question, what is does it go up to first? Do you guys do this? I'm unsure about these topics. Superposition and source transformations. I'm not sure if you guys cover them, and then I'm not sure if you guys have gone up to first order circuits. All right, pretty much that. Okay, so these three I'll save till the end because I don't quite know Dr. Chiu's syllabus by heart, but the rest of it I'm very confident is on your first test because I'm pretty sure it's been there for a bit before. Also, the syllabus changed with the snowstorm. Right, so let's start talking about just circuit elements. And you did superposition? Excellent. I'll cross the question mark off there. Okay, let's talk about circuit elements just as a quick reminder. When we're solving circuits, what we're interested in? 3 things, right? We're interested in voltage. And what I want to note with voltage is that in the physical definition, mathematicals, we don't really care about that for this class. What we do want to know that voltage is relative, it's electric potential, right? So your voltage application is always in reference to 0 volts, which we call ground. So just remember that voltage is a relative quantity. And voltage across an element means if you have some element, it's going to have a plus and minus terminal defined. And this node can be called node A and node B. So the voltage across element I is going to equal the voltage at A minus voltage at B. This is important to know and consider. It comes up all the time in node voltage. I see this concept not fully understood a lot. Current. We all know what current is, right? It's a charge flow. Current is directional, right? So we'll denote with a vector. And current can be defined going anyway. But when you talk about current, you define it as going one way. If you get the current equals some negative number, that just means it's really going the other way from its definition, right? So if let's say I, in this case, as defined, was negative 4 amps, I could define I as being positive 4 amps going this way. It all depends on, once again, the relative definition of what you've put down. And the third thing we talk about is power. Well, the third thing we care about is power. And power is defined as I V, and using Ohm's law, of course, you can get this equals I squared R or V squared over R. Power can also has a relative thing to it, as everything does, but in power there's a very specific convention called the passive sign convention. So there's positive and negative power, but if we have some element, once again, it has positive and negative terminals defined. If current is going into the positive terminal, we call this positive power. It's defined as positive power in this convention. And likewise, if we have a negative terminal and we have current entering the negative terminal, it's defined as negative power in the passive sign convention. And we call positive power, this is absorbing, and negative power is delivering. And as a quick note, resistors always absorb. So you would make their same thing. Absorbing power, dissipating, delivering power, your charging power. Dr. Chiu may call it that. And yeah, so resistors always absorb, so you draw their terminals accordingly. Also, in this class, the sum of your power has to equal 0, right? You can't just create power from nowhere. Power is delivered to the circuit, and then all that power is dissipated in the circuit. It goes away. We deliver this energy to the circuit through sources, right? So let's talk about some sources. If you remember, a voltage source, this keeps a constant voltage across its terminals. If this V, let's say V equals 5 volts, we'll call this node A, and we'll call this node B. If we V equals 5 volts, the voltage at B equals VA plus 5. It does not equal 5 all the time, right? It's going to equal 5 commonly because we usually define something like this as ground. But keep in mind that it depends on what's at VA. It's not just equal to 5. Those are two different things. Something else to note. Voltage sources in series, they add. This is okay. Voltage sources in parallel, while theoretically possible, isn't practically realizable. These things blow up. Because what happens if you have V1 and V2, and V1 doesn't equal V2? Then what's the voltage up here? Yeah, it's bad. Don't do this. But voltage in series source, that's perfectly fine. Current sources. Like the voltage source kept a constant voltage between its terminals, current sources keep constant current. And it flows through in the direction of the arrow, right? It's a bit simpler. Something to keep in mind here, what the voltage source is that voltage sources, this time current sources in parallel, they're great. You can do this. They'll add. Current sources in series, on the other hand, they will blow up. Because if I1 does not equal I2, then what's the current in the branch? We don't know. Don't do it. These are the ones symbols I've drawn here, as you should know, are going to be your independent sources. They don't care about the rest of the circuit. They always do their job, which is keep a voltage or keep a current. You can also draw the same symbols with diamonds. So like this, or like this. And these are dependent sources. And you're going to see them with like an alpha V or a beta I, something like that. They're a constant. This constant is going to depend on another area of the circuit. But other than that, they act the same way. They keep a constant current or a constant voltage. It just so happens that the value they provide is dependent on another area of the circuit. Only difference. Okay, let's move on. Talk about Kirchhoff's laws. Let's start with KVL, Kirchhoff's voltage law. So Kirchhoff's voltage law is the sum of the voltages around a closed path is equal to 0, right? Fairly simple. So let's talk about, let's just draw an example. Right? And let's say we have, I don't know, V1, which is minus, and V2, and V3. Right. If we want to write a KVL expression for this, we need to first assign a convention. So there are two ways to do this. I'm going to start from here and go here. So I'm going to be causing drops like this. There are two things you'll see. You'll either see going from a plus to a minus, a voltage drop, or you'll see going from a minus to a plus, a voltage rise. One of them has to be positive and one of them has to be negative. And you can do whatever you want as long as you stay consistent. As far as what I'm going to use, I'm going to say that these drops are positive and these rises are negative. So if I'm writing my sum of the voltages around this loop, it's going to be, we're going from a plus to a minus in V1. That's a voltage drop. That's plus V1. We're going from a minus to a plus across V2. That's a rise. That's a minus V2. We're going from a plus to a minus across V3. That's a voltage drop. That's a plus V3, and that equals 0. And then that's Kirchhoff's voltage law. We walked around the loop, and we summed all the drops and rises, and knowing this information, we could now solve various things in the circuit. KCL, Kirchhoff's current law. Similar but for current. If we have a node, and we have some current going into I1, I2, and I3, it's the sum of currents in and out of the node are equal to 0. And once again, as convention, you can either be going into a node or you can be going out of a node. Oh yeah, that's a good question. So for resistors, because resistors always drop, right? Resistors are always drops, like we said before. The way you define your current, that's the plus and minus, right? Voltage sources will have a plus and minus on them. Current sources, you can just define it. What's actually kind of cool about these laws is that it doesn't really matter how you label it initially. Let's say, for example, and we'll see this in Kirchhoff's current law too. Let's say, for example, that I, as a fool, labeled this plus and minus, when in reality the current is going this way. The math should turn out that I'm going to get a negative voltage here. So what my math will tell me is that the voltage from A to B is negative, which means it's really a positive voltage going like this way, like it should be. So your math should correct your mistake. So the answer is label it whatever you want, and your answer should turn out the same. Just keep your labels there so you know, so the negative makes sense. You can't flip-flop. Just know what, just keep it there. If that answers your question, you can say so. So for Kirchhoff's current law, I'm going to define going into a node as positive, and I'm going to define leaving as negative. This makes most sense to me. And likewise, here we can do the sum of I equals I1 plus I2, minus I3 because leaving, right, equals 0. And to build upon your question, let's talk about the same thing with current. What if I define it like this? Is this possible? Very clearly not. It's not possible, right? You can't have all the current going to the node. But the math will turn out that one of them, let's say I3, will end up being a negative number, which means that it's really going this way and your intuition will check out. So for Kirchhoff's current law, you can define the current going anywhere you want. The math will check out and you'll get a negative somewhere to make it realistically possible. Just make sure, like I would recommend physically drawing in current arrows when you solve circuits so that you remember which way you define the current is going. And we'll come back to this in node voltage when you're doing a lot of that stuff, right? Okay, let's talk about resistor networks. Resistor networks, everyone knows what a resistor is, right? A resistor, we all know this squiggly line symbol. It's a material that impedes the flow of current. We measure in ohms. We give it a resistance value in ohms. Oh, that's a terrible. In ohms, right? Ohm's law gives us the relationship for resistance, current, and voltage, right? We say that V equals IR. Very nice. That's just a reminder. You should really know this. We can combine resistors in series. If there's a bunch of them, right, this can be turned into a resistance equivalent, which equals the sum of all the resistances, sum over all N, right? And if they're in parallel, so as far as formal definitions, resistors in series, if things to be in series have to be joined at a node and only those two elements. So there's another element here. These two are no longer in series. So if the only two elements in the node, they're in series. For parallel, they have to start and end at the same node. So if I'm here, and I go here, all these three are in parallel. If I start R0, Rn, and I can also turn this into an equivalent resistance. But this time, the equation is 1 over equals the sum of 1 over all of these resistances, right? And they have to start and end the same node. We can get some crazy stuff, like if you have a node here, which is like this may look really crazy, but they all start at node A and they all end at node B, right? So you can redraw this as they're all in parallel. So if you're ever unsure, look at the two ends of the node to make sure things are in parallel. Do you guys talk about the delta Y circuit configurations? I don't think the ENA classes in electrical engineering tend to talk about it, but I could be wrong. I'm going to start it anyway. Only in the book? Oh, excellent. I disliked them. So, oh, you did? Had homework? Oh, okay, you had homework. Okay, never mind. I will talk about them. Okay. If you had homework on them, we might as well talk. Although I doubt Dr. Chiu will give you a problem on it, but it's helpful to know. So the delta Y are the appropriately named. Here's the appropriately named delta. I mean, unfortunately, there's not much. This is just memorizing a bunch of formulas. What the theorem says is delta Y. I mean, if they're important for power electronics, so if you plan on going to power, know these things. It says we can go from a delta to configuration. This is a delta, right? We can go from there to a Y, and a Y looks like yes, these are Y circuits, delta Y circuits. Where these nodes are like this. I had my formulas wrong earlier, so I hope I corrected it. But if my notes are correct, if you're going from delta to y, you want to solve for R1, R2, R3 based on RA, RB, RC, right? So R1 is going to equal RB, RC over RA plus RB plus RC. R2 is going to equal RC or RA over that same denominator. And R3 is going to equal to RA, RB over that same denominator. And then for y to delta, RA is going to equal R1, R2 plus R2, R3 plus R3, R1 over R1. RB is going to equal that same numerator over R2. And RC is going to equal that same numerator over R3. I mean, you can look at the derivation, but you should probably just write these down in your cheat sheets if they ever come up and apply them if needed. They're very helpful to solve certain circuits. You want to recognize when turning a delta into a y can help you. But other than that, that's about it. Let's move on. Talk about something a bit, voltage dividers. This is important to know conceptually because it lets you do a lot of things in your head. So when resistors are in series, the voltage across the entire network in series divides itself among each component, but the current stays the same. So to find the voltage across any one of the resistors in series, we can find a ratio. We can say that the voltage across resistor I, let's say, is equal to the V total across the entire resistor in series times that resistance over the series resistance. I'll back to the equations. I would advise looking at, I mean, you can rewind this, can't you? But yeah, you can always, I would recommend using your book for the equations. I think I had these wrong in one of the versions of my notes, and I forgot which one it was. So confirm with your textbook that these are the right equations. I don't use them often. And the handwriting will be neater than mine. But yeah. So we have V total Ri over R equivalent, right? And this equals, in this case, it's V plus minus V minus. Ri is the same, and this is going to be the sum of R's, because this is the resistance equivalent in series, right? And this is the general case, but you'll usually see this with only two resistors. So if you have something like this is where you'll see it a bunch, right? You have two resistors, you have R1, you have R2, I didn't write R2, and you have V1, and you have V2, right? And you have some V across it all. You can say that V1 is going to equal to V times R1 over R1 plus R2, following this formula. And V2 is equal to V times R2 over R1 plus R2, again, following that formula. So this is what you'll see most often, but remember that it can be applied generally to any n resistors in series. They can be an infinite number, doesn't matter. All right, a current divider. So much like how when resistors were in series, the current stayed the same but the voltage divided up. When resistors are in parallel, the voltage stays the same but the current divides up. So we're going to have some total current coming into this parallel combination of resistors. And to find the total across any branch, we can say that the current through, say, branch K is going to equal I total coming in times the opposite of resistance, R equivalent over RK, because more current will go where there is less resistance. And so this is going to equal, 1 over RO plus 1 over Rn, and then times R over RK, which we're trying to find the resistance of. So this is in general, right? And much like the voltage divider case, you're going to often see the case where there's only two of them in parallel. A current divider like this has some I, we'll say I1, we'll say I2, and R1, R2, and following this formula, that's not a good I1 is going to equal big I times R2 over R1 plus R2, and I2 is going to equal big I times R1 over R1 plus R2. Notice that I1 has an R2 in the top, and I2 has an R1 in the top. It's the opposite, right? And you can get these by following these formulas. Okay, so that's everything for, I guess, chapter 1 in the background stuff. We're going to move on, to the big circuit analysis technique, probably one of the more important ones, node voltage. So keep in mind, this is based on Kirchhoff's current law. So you kind of need to know KCL to be able to do this. I've broken down how I approach these problems into a couple of steps. And so here they are outlined. One, you're going to want to ID your essential nodes and combine when possible. This is just to make things easier. Two, you're going to choose a node as ground. Remember, everything is relative, so you can choose ground, unless he gives you ground, in which case, go with whatever he gives you. But if he doesn't, you can choose whatever you want as ground. However, there are smart decisions for ground, and there are dumb decisions for ground, and the smart decision for the ground is usually fairly obvious. But still, it's helpful to identify one as ground. Three, you want to write KCL equations for each node in terms of V. So what do I mean by in terms of V? So we have a resistor, right? And let's say our KCL, we're writing it for VA, right? And there's some VB over here. And we have an R. We define our current going this way. At node A, we say that negative I, because leaving node A, and there's a bunch of other stuff, equals 0, right? How do we write I in terms of voltage? I equals V over R from Ohm's law, right? This V is really the change in V across resistor over R, right? So if we go back to here, this I can be written as VA minus VB, this is the change in V, over the resistance, R. And it's the same thing, and note the thing that came first was defined based on our current. If you remember back to what I was talking about definitions, because current's going this way, here are your terminals. Right? If current was defined the other way, and you would choose this, right? You would say that, okay, I have arbitrarily chosen current to go this way. Then your terminals are like this. And then your equation would be switched. It would be VB minus VA over R. But it doesn't matter because your equations will all turn out to be fine, and this will be negative or positive depending on whatever your actual answer is, right? Okay, and once you have all that, you're going to have a system of equations. So just solve the system for the node voltages V. And as a caveat to this, if you have the dependent sources, you won't be able to just solve the system immediately. So you're going to want to express the dependent source in terms of node voltages. And then you can solve. Okay? So these are the steps that I would recommend you use, or some combination. This is the general flow, right, of how you solve node voltage problems, or how I solve them. So let's do some examples now. We've been talking a lot. Haven't really done any actual analysis. So let's say we have a circuit that looks like this. 100 ohms. And then I'm just gonna, also, if you can't read anything, I apologize. My handwriting is absolute garbage. That should be ohms. and this should be 12 volts. Okay, so here's our circuit, right? And the question will be solve it using node voltage. So how do we start? First of all, we identify our nodes. First of all, can we combine anything? Yes, we can combine these two. This can just be one resistor. So let's do that. Let's 300 plus 100. We combine them in series to make 400 ohms, and this resistance goes away. So there, we have made the circuit simpler for ourselves. Because less nodes is one less equation to solve. Now, I think you should I recommend drawing in your currents, right? Oh, right. You should also identify your nodes. Let's call this node A. Let's call this node B. Let's call this node C. Let's call this node D. And let's define node D as ground, because it's the bottom of this voltage source. It's at the bottom of this voltage source. It's a convenient place to put ground. Let's define our currents. I1, I2, I3. Like I said, is this physically possible? No. Does it matter? No. It'll all come out when we solve the circuit, which we will see. Okay, so let's start writing KCL for each node. Let's start with node A. Looking at node A, I actually don't need to write KCL. Remember, we're solving for node voltages, and we can just look at it and say VA equals 12 volts. Because there's a voltage source of 12 volts between node A and ground. So we can immediately solve for node A. Excellent. Node B. At node B, I'm going to write KCL as the sum of the current. It's going to be I1 plus 0 equals I1 plus I2 plus I3, right? And now I want to define these currents in terms of voltages. So this is going to be VA minus VB over 100, going from here to here. I2 is going to equal VC minus VB over 400, going from here to here. And I3 is going to equal VD minus VB over 200. And remember that VD is ground, so this is a 0. And this equals 0, right? And for node C, that's what we did. That's why I drew the ground symbol there, because we would define node D as ground. And that's what you should do, yeah. It's the correct choice. Okay, so looking at node C. Just like node A, there's a voltage source in between it and ground. So, 6 volts. So now we have one equation, we have one unknown, because we can put VA in here, we can put VC in here, and we want to solve for VB. So when we do that, we get that VB equals 54 over 7 volts. I'm not gonna actually solve, like do the math. I assume you guys can do the math. The ENA part is setting up the equations. So you could solve this using whatever. Why do you subtract VC minus VB? Ah, yes. Okay, that's a good question. It's because I defined the current as going this way. So because the current is going this way, that means my terminals have to be here. And so the voltage across here would be, in the direction of the current, would be VC minus VB over 400. If I had to find the current as going the other way, I would do VB minus VC. But I didn't. I defined it as going this way. Okay, that's that question solved. Let's move on to something more difficult. Let's say you have a circuit that looks like this. Okay. And I should probably write in values. 1 ohm, 2 ohms. And this is going to be 3ix, where ix is defined as here. And this is going to be 2vy, where vy is here. So now I use some dependent sources, makes it slightly more difficult to solve, but our process will stay the same. So let's ID some nodes. I'm going to call this A. I'm going to call this B. I'm going to call this D. I'm going to call this C. I'm going to call this E. And that's all the nodes. You can't combine anything. There's nothing in series or parallel. I'm going to label node E as ground, right? And I'm going to draw my currents now. So I'm going to say we have I1 going this way, I2 going this way, I3 going this way, and I4 going this way. Note that all the other branches, I guess you could have I5 going this way. Notice that all the other branches already have a current defined. There's a current source here, there's a current source here, and Ix is already given to us. So that's all the currents I'm adding to the network. So let's write system equations at each node. So starting at A, we can see that writing KCL, we get I1 minus I4 minus 9, right? And these two are minus because they're going away from the node in my convention. And this is going to equal, when you write it all out, I1 is going to turn to VC minus VA over 2. I4 is going to be VA minus VB over 1. And minus 9 is just minus 9. Nothing's changed there. That's A done. Let's do B. At B, we can see that we have I4 going in. We have plus 2Vy, because that's the current going into it. And we have I3 going out. This equals, we know what I4 is. I4 is VA minus VB over 1. We don't know what Vy is right now, so we'll just keep it as Vy. And we'll subtract I3, which is, well, we also don't know what I3 is. We're just going to keep it as I3. Because we can't do we can't do Ohm's law with the voltage source. So we're going to have to leave it like that. C. Node C, we can see that there's a 2-volt source between it and ground. So VC equals 2 volts. Very nice. At VD, we have IX, I2, and I3 going in. So 0 equals I2 plus I3 plus IX, right? I2 is VC minus VD over that voltage value. We're going over here, I2, over 1. The resistance value, sorry. And then plus I3, which again, we don't know what I3 is, so we're just going to write I3. And we're going to subtract IX. And IX can be, and IX is, we're going to add IX. I don't know why I said subtract. And IX is going to be ground, so 0 minus VD over that resistance, which is 2 ohms, right? And that is all of our node voltages, right? Let's stop and evaluate what we have. We have unknowns. So how many unknowns do we have? We don't know VA, we don't know VC, we don't know VB, we don't know VY, and we don't know I3, right? And how many equations do we have? We have 3. So we have 3 equations, 6 unknowns. That doesn't track. So we need to somehow get these two terms in terms of VA, VB, and VC, and then we're golden and we can solve. Let's start with VY. How can we write VY in terms of node voltages? Let's look at node VY. What is VY? VY is VC on one end and VA at the other. So VY is VC minus VA. Does that make sense? So if we substitute that in for VY, VC equals 2 volts, correct? Oh yeah, you're right. So you just, this is 2 minus VA. But yeah. And notice I didn't put down VC as one. Oh, I did put down VC as one of my unknowns. Let's ignore that. Good catch. VA, VB. We don't know VD either, right? Yeah, this should be a VD. There we go. So still 6 unknowns. I just switched one. VAB, C, D. Okay, yeah. Now we're good. So yeah, we have written VY in terms of our unknowns now, which is good. So now we need to work on I3. I3 is going from node B and node D. Really not a way to put that in terms of node voltages explicitly. So what you can do is you can notice that for stuff like this, VB and VD are, if you add them, I3 will cancel. So let's add them, VB plus VD. And you're going to get VD minus VB plus 2 VY plus VC minus VD minus VD over 2, and I3 is gone. Now I3 is no longer an issue. VY is no longer an issue. You now only have 2 equations, but you still have 3 unknowns. So you need to find a relationship between VD and VB. And you can see that VD and VB have a voltage source in between them, right? So we know that VB, and let me write the situation here. We have D, we have a voltage source, and we have B, and this is 3Ix. So VB plus 3Ix equals VD. What's Ix? VB plus 3, looking at our table again, it's going to be, or our circuit, Ix is ground minus VD. So plus 3 times negative VD over 2 equals VD. When you solve, you're going to get that 5 over 2 VD equals VB. We now have a third equation with 3 unknowns, and we can solve. Let's just go into 8. I think I planned for 2 hours initially. And so now we can solve everything, getting us VA equals negative 2, VD equals 2, and then VB is going to equal 5. Right, and then you solve it, and that's all of it. So yeah, that was a more involved node voltage problem, and that's all I have for node voltage. So we're going to move on to mesh current. Okay, mesh current. So this is based on KVL, and the steps I'm going to outline: 1, ID your meshes. It's not legible. ID your meshes. Simplify your components. Right. And then 2, you're going to define some mesh current going in the same direction. So choose, you're going to choose either clockwise or counterclockwise, and you have to stay consistent with that. Otherwise, it's just wrong. And then 3, much like we wrote KCL for no voltage, write some KVL around each mesh. For example, and in terms of current. So for example, let's say we have a mesh intersection here. I1 is going here. I2 is going here. I tend to draw my meshes going clockwise. You can do whatever you want. And this is R. If we were writing from mesh 1, we would write this mesh as it's going to be R, it's going to be V across R, right? From I1's perspective, this is the voltage across R. So we can say this is, not I1, R times, using Ohm's law, V equals IR. It's R times I1, means I1's going the correct way through R in our definition, minus I2, going the wrong way through R in our definition, right? From I1's perspective. If we were writing the same equation from I2's perspective, I2 is going this way. It thinks this way is correct. So now the voltage across R looks like this. So VR is going to equal R times I2 minus I1. It depends which mesh you're writing for. This distinction is important. It's not intuitive either, so make sure you remember it. And for solve systems, and if you have dependent sources, same thing as we did previously. Okay, let's do an example. Let's say we have a circuit that looks like this, and I will draw it. So I'm not going to write the ohms. I'm just going to write the value. And this is going to be 4 volts. Okay. And so now let's define our mesh currents going clockwise, because that's how I like to draw them. I1, I2, I3, and I4. Okay, so we have our mesh currents. Let's write some system equations for them using KVL. So let's start with I1. Now, if you remember from when we were doing no voltage, we could sometimes shortcut this step if we knew what that node voltage had to be. There's a similar thing for mesh current where, let's look at I1, where we're going this way. The current through this branch is only I1. Well, the current to that branch also has to be 2 amps because of the current source. So we can just write down that I1 equals 2 amps, and then we're done. It's very nice. Okay, I2. I2 you have to do some actual work. So let's go and start here and go up here. So 0 equals the voltage across the 2 resistor, plus the voltage across the 4 resistor, plus the voltage across the 3 resistor, because I call voltage drops positive, and every resistor drops voltage always, right? Let's write this as V2 is 2, the resistance, times I2 minus I1, because we call this way positive when we're solving for mesh 2, plus 4 times I2 minus I4, plus 3 times I2 minus I3, and this is going to equal 0. And that's our equation for I2, and you would multiply it out and simplify, but I'm not going to do that because that's just algebra. I3. So if we look at I3, it's just like I2. I3 goes here, here, and when it gets over here, it's the, when it gets over to the right-hand side, it's the only current running in this branch. So it has to be that branch current. However, it's defined the opposite way. So we're going to say that I3 equals negative 4 amps because it's defined in the opposite way as that current source pushing 4 amps up. So the don't need to write system, we can just say what it is. For I4, we're going to have to write a system of equations. So 0 equals V4 plus V1. Now this voltage source is, when we're going this way, right? We're going from negative to positive. That's a voltage rise, and if you recall, I define voltage rise as negative, so minus 4, and then plus 2. And so voltage rise for the 4 ohm resistor, man, 4 times I4 is now the positive current in this domain. I4 minus I2 and plus 1 times, it's just I4 up there, minus 4, and then in this 2 ohm resistor, it's just I4 there too. And so now we should have 2 equations with 2 unknowns. We don't know what I2 and I4 are. And so when you solve that using your favorite method of system equations, solutions, whatever you prefer, you're going to get that I2 equals negative 0.85 amps, and that I4 equals 0.85 amps. Oh, no. Sorry. You get that I4 equals 0.085 amps. And that's what you get. All right, pretty simple. Let's do another one. So example 2 for mesh current. If you have any questions, feel free to spit them out. Okay, I'm just going to call this ground. 50 volts, 2 ohms, 5 ohms, 4 ohms, 20 ohms, and this current on the right is 1.7 V delta. What is V delta? This is V delta. Oh, this is 9 I delta. What is I delta? This is I delta. Okay. Oh, let's define our mesh currents. We're going to go this way, and this way. I1, I2, and I3 respectively. And then we're going to write our system equations for each one. So, for I1, right, we're going clockwise. We go up in 50. That's a voltage rise, so that's a... No, this is not the 2310 review. You are in the wrong place. The 2310 review, I think, isn't happening. I think there you can look at past videos. Oh, actually, no, 2310. I think that was yesterday. Yeah, you're gonna be very confused if you're here for 2310. Look in the YouTube channel and see if you can find the review, and it's gonna be called Digital Systems, I think. That's the name of the course, right? It was streamed like yesterday, so you can just rewatch it. Okay, so I1, Right, where was I? I was at minus 50. Minus 50, and then we're going across this one, so we're going to do plus 2i1, and then we're going to do plus 4 times i1 minus i2, and then we're going to do we have this voltage source here, right? And it's a voltage drop, so it's going to be positive plus 9i delta. Okay, let's do for I2 now. So starting at the I delta, it's a voltage rise from the perspective of I2. It's going to be minus 9i delta. Oh, sorry. Yes. Yeah. Voltage rise minus 9i delta, and then plus 4 times I2 minus I1, plus 5 times I2, and then plus 20 times I2 minus I3, right? It all equals 0. I should probably write this equals 0 as well. And then I3 equals, well, actually I3 we can do something special here, right? We can say that in this very rightmost branch, I3 runs exactly on the line of the current source, so I3 has to equal 1.7 V delta. Okay, so let's review what we have. We have, once again, 3 equations for each mesh current, but we have a bunch of unknowns. We have I1, I2, I3, V delta, I delta. Well, there's 5 unknowns. So we need to solve for V delta and I delta in terms of I1, I2, I3. The picture's a bit dark. That's going to be streaming quality. I mean, I don't think I can improve that. I use a dark background because I like dark mode, but since I'm writing on white, it shouldn't be an issue. Yeah, so anyway, V delta, I delta, we need to solve for those in terms of I1, I2, I3, right? Then we'll have a nice system of equations and we can solve. So, V delta. How do we solve for V delta in terms of I1, I2, I3? Well, we can use Ohm's law. V delta equals the current across a times resistance. What's the current? I1. So V delta equals 2 I1, right? Okay, nice. Now what about I delta? I delta, when we're moving this way, I delta is running the same branch as I2. So I delta is really just I2. And just like that, we have a solvable. Oh, really? I didn't do anything. I delta and I2, they're the. Now we have system equations. And when you solve it using your favorite matrix solving method or favorite system solving method, I1 equals negative 5 amps and I2 equals 16 amps. And I'm not going to actually solve for you since that's math. All right, that's mesh current. So now we're done with mesh current on no voltage. We're going to move on. Let's hold on. I don't remember. Let me look up. So we've done this, and this. Oh, I guess next is Devin Norton. I will do superposition first because that's what I usually do, and then we'll finish off with Devin and Norton. All right. Let's do superposition. Okay, so what is superposition? Superposition, for all you guys who are taking signal systems, this is actually fairly familiar to you. It's a property of LTI systems, right, which says that f, so some function that's made of a bunch of added inputs, right? It says that this can be decomposed into this. That's the mathematical definition. But what does this mean for us circuits people? Well, it basically means that the output of the system with all inputs applied is the same as all inputs applied separately and added up. So if we have circuit is system, where system of resistors, right? And the input to that circuit, we're going to call sources. And the output of that circuit is going to be voltage slash current slash power, right? So what we want to do is we're saying that this complicated circuit with a bunch of sources active at once, if we could somehow solve for each of those sources separately, we can get the answer by just adding them all up. To do that, we need to somehow get rid of sources. And so we're going to deactivate them to do that. So step one, you're going to deactivate all sources but one. You're going to solve for f of x1, x2, whichever one you're solving for, deactivate the rest. The question is, how do you deactivate it? Well, for a voltage source, an ideal voltage source, we know it carries a constant voltage across its terminals. But if we want to deactivate it, we want that voltage to be 0, right? No voltage across its terminals. So it's going to be a wire. A wire has no voltage across its terminals. So you're going to change voltage sources into wires to deactivate them. For current sources have a constant current. So to deactivate them, we want 0 current. And what has 0 current? An open has 0 current going through it, right? So this is how you deactivate the two sources you'll see. And then 2, you're going to solve the circuit as you would using any other method you want. You're going to find the output you're looking for. You're finding f of xn, right? And then 3, you're going to repeat 1 and 2 for every single source. And then 4, you're going to find f of x equals f of x1 plus f of x2. Basically, you're going to add up all the outputs you found earlier to get your final answer. Okay? Yes, so you add everything up and you find out. So it's a very handy concept that can. So let's do an example where we're going to use superposition to make the problem slightly easier. So the question is going to be you're going to find I of x. What's I of x? Well, we need to draw the circuit first. So we have this. We have this. We have this. This is the circuit. 4 ohms. I'm not going to write ohms. Too much work. 2, 1, 3, 5 volts. And here is our I of x. And then we're going to go here, here, and then ground it. And this is going to be negative 3 amps. Okay, so this is the circuit. Find I of x. And we're going to use superposition to do this, because that's the topic. You could solve it in a variety of ways, right? But we're going to choose to use superposition. So let's start by deactivating one of the sources and then solving for the other. What do we choose to deactivate? Well, let's choose the current source. Let's get rid of the current source. So when we get rid of the current source, remember, it turns into an open circuit. Oops, wait, sorry. It turns into an open circuit. So now we're just left with this side, and we need to solve for Ix. Let's redraw this. First of all, the top things can just go away since it's all open, right? So we're left with this. This is kind of a mess. Let's redraw it in something that looks more palatable to us. So first of all, we notice that we can combine these two and these two in series, right? There's only one node between them, and that node goes nowhere else. So we can redraw this as and we add 2 plus 4 is 6, 3 plus 1 is 4, 5 volts is still here, and we still want to solve for Ix, right? Okay, and so now let's redraw it again to make it more familiar to us. These are all in parallel, right? So we can solve for the equivalent resistance in parallel. 5 volts Ix, and the parallel resistance when you do your parallel formula is 2.4 ohms. Now we can use Ohm's law, and we can find Ix1 as equal to 2.053 amps. So we found half the solution, right? We found IX1. But now we need to find the same thing, but with the voltage source deactivated. So let's deactivate the voltage source and then redraw the circuit. So I'm going to put the current source back. And this time I'm going to get rid of the voltage source. And remember, the voltage source turned into a wire like this. So this is kind of tricky, right? This is a current going across a wire. Does that make much sense? It does, but we need to kind of approach it in a haphazard way to actually solve the correct current. So if we use KCL here, then we can solve for IX. And to do this, we'd want to know the current across either of those resistors. To do this, I'm going to combine, I'm just going to move it over here. I'm going to combine this circuit, I'm going to combine this node into one thing and add up these things in parallel on both ends. When I do that, I'm going to get a circuit like this. Accidentally erased all that, right? And now using Ohm's law, I can calculate the voltage across these resistors. And when I do that, I find that this voltage is negative 4 volts. And I find that this voltage is negative 2.25. And when I go back here, now I know the voltage from here to here is negative 4. And the voltage from here to here is negative 2.25. So I apply Ohm's law again. I find IX1, I find I2 and I3, and I say that, I write KCL. I say that I2 minus IX minus I3 equals 0. I2 is negative 4 ohms, negative 4 volts over 2 ohms minus IX minus I3 is negative 2.25 over 3, or this is V over R. And when I solve, I got IX2 equals negative 1.25 amps. And so now it's time to find the final answer. We know that from superposition, the property that IX equals IX1 plus IX2. So this is with the voltage source. This is with only the current source, and this equals what was IX1? IX1 was, oh, it's right here. 2.053 minus 1.25 equals 0.8333. That's the answer. All right, so that's superposition. Deactivate sources, then solve for it in any way you already know how to, and then add your answers all up to get the actual true answer of the whole circle with everything applied. Okay, let's move on. The last topic, I guess. Thevenin and Norton equivalence. These are very important. So, the whole concept behind Thevenin's theorem is to simplify a circuit. We can turn different sources or pairs into each other. So basically, let's say we have a circuit. We're going to call this circuit a mess. This circuit has some output across terminals A and B. Yeah, this will be uploaded. It should be uploaded automatically. I don't think I have to do anything for that. Yeah, so we have a mess. This circuit, this mess of a circuit is uploaded, and it's not uploaded. This circuit is here, and it has some output across A and B. Thevenin's theorem says that we can turn this into a Thevenin voltage, a Thevenin resistance across those same terminals, and the effect is exactly the same. And And then alternatively, we could also turn into a Norton equivalent, which is just in this configuration. This is R Thevenin, this is I Thevenin, and you convert using Ohm's law. Can you use superposition when there are dependent sources? Huh. I don't think you can deactivate a dependent source quite like you can independent sources. Dependent sources don't deactivate quite as well because their values depend on other values in the circuit. So I don't think you can just eliminate them. I'm not quite sure if I'm being honest, but I wouldn't try it. I'd look it up somewhere else. That's a good question. I know you can't deactivate them. Like, for example, as we'll see here, when we're solving for Thevenin and Norton equivalents, when we're solving for the R Thevenin, you end up deactivating sources, just like you did for superposition, but you can't deactivate dependent ones. So I'm going to guess that it's the same thing for regular superposition. It's not quite an independent input. It depends on something else in the network. But okay, yeah, so we have this is Thevenin. This is Norton. They're the same thing. Okay, and let's also note that if you have like a Thevenin equivalent that looks like this, this is R1, this is R. The parallel resistance is absolutely nothing. You can eliminate it, and the output is the same. And in the same manner, a resistor in series with a Norton equivalent like this, this can just be replaced like this with no effect on the output. They do not matter. Okay. Let's talk about some steps. I can't just move on yet first. So, right, for these we're trying to find V Thevenin, R Thevenin, and I Thevenin. So let's talk about how do you solve V Thevenin for a circuit. So for V Thevenin, we're going to say for our terminals A and B, you're going to place an open circuit between terminals A and B and solve for the voltage across the open circuit. Conceptually, you could think of this as a case of there being an infinite load at the terminals. That's an open circuit. And the voltage across the open circuit has to be V Thevenin. And you will solve for it using any techniques you know. For I Thevenin, you're going to place a short circuit. This is a special case of zero load. And you're going to solve for the current through the short circuit that is your I Thevenin. And here you have the open circuit equals V Thevenin, right? And so you can solve them like that. R Thevenin is going to deactivate all independent sources, not dependent ones. You're going to place test source at terminals, and you're going to solve for B test over I test that equals your R Thevenin. Practically, you only need to solve for 2, right? Because if you know V Thevenin and I Thevenin, you know R Thevenin through Ohm's law. So if you know 2 out of 3, you know all 3 and you're all set. But I'm going to go through solving all 3 because sometimes it's easier to solve for one or the other, depending on your circuit. Okay. Let's do an example. So let's say that we have a circuit like this. Actually, hold on. Let me ask the original problem. Let's say we have a circuit like this. Now, I think I saw on Dr. Chiu's sample exam, he actually had a question involving Thevenin that needed you to use a concept like this. So I'll talk about it in here. Okay, and the question is, find I/O for any R. And we could do this in a number of ways, right? We're going to choose the power of Thevenin equivalence. We're going to say, okay, R is our load. Let's remove it from the circuit for now. R is gone. R is our load. I/O is gone. This is our circuit now. We're going to solve for a Thevenin equivalent and then put R back in, and it'll be the exact same thing as if it was there the whole time. Right? So let's solve for V Thevenin now. So V Thevenin, remember how the circuit is an open circuit. It's already an open circuit, or it looks like that, so we can solve normally. This is V Thevenin. We can notice that V Thevenin equals the voltage across the 2 ohm resistor, and the voltage across the 2 ohm resistor is given by Ohm's law. It has 1 amp running through it. So this equals -1 times 2 is equals -2 volts. So V Thevenin, very easy to solve for, -2 volts. Okay, what about I Thevenin? For I Thevenin, if you recall, we short the terminals, so there's a short circuit, and we want to solve for the current of that short circuit. Well, because this is a short circuit, it shorts out the 2 ohm resistor. All the current goes through the short circuit. What current? -1 amps. So I Thevenin just equals -1 amps. Now from this, we can say that R Thevenin equals V Thevenin over I Thevenin, which equals -2 over -1, which equals 2 ohms. But for practice, let's solve it directly as well. I'm going to redraw this circuit with the sources deactivated. That source on the left, that voltage source, let's deactivate it and make it a wire. That wire then comes over here, and there's this resistor here, right? There's a current source up there, which is now an open circuit, and it leads to terminal A. Then there's a resistor on the bottom, a resistor up here, and we have our terminals A, B. And this is 6, 5, and 2, right? So in the procedure, we said that we want a test source between A and B. And we want to find I test, we want to find V test over I test, right? Let's follow the current. I test goes here, it goes here, it can't go here, so it goes here. This is really just and it's pretty simple to see that V test or I test is going to have to equal 2. Right? So it's the same thing as we got earlier. So that's the Thevenin equivalent. Let's do a harder example, and then we'll, I guess, end things, right? Since that's all that's supposed to be covered, as far as I'm aware. Okay. Oops. Okay, yeah. Let's do a more. Oh, sorry. That actually isn't the end of the problem. We found a Thevenin equivalent. We need to solve for I/O and R, right, at the very beginning. So let's do that. So let's draw our Thevenin equivalent. Our Thevenin equivalent is -2 volts with a Thevenin resistance of 2 ohms. And now we have A and B, but we had R, our load, between those terminals, and we want to solve for I/O. Well, now this is very simple. This is just Ohm's law. I/O equals V over R, which equals -2 over 2 plus R. So for any R, we now know I/O, and the problem is solved. On Dr. Chiu's sample exam, he asked something similar, or he hinted at doing something similar when he said to use a Thevenin equivalent around something. I forgot what it was. I'm pretty sure it was there. Okay, let's do another example. And the question this time is to find the Thevenin equivalent of the circuit. I'll draw my values. Yeah, okay. So that's the whole circuit. We want to find Thevenin equivalent. So, solving for V Thevenin. Solving for V Thevenin. We want the open circuit voltage. So we want that V is going to equal the voltage across the 5.6 k ohm resistor, right? So we need to solve for that node. We can solve this in many different ways. I will choose to use node voltage, but you could do whatever you want. Okay. So let's use KCL to write some equations. So at I'm going to label some nodes. X is going to go here. I think I'm going to call this Y. I'm going to call this I1. I'm going to call this I2. I'm going to call this I3, and this REI delta. And so then using our node voltage, which we should know very well now, at node X, there's a 280 volt source, and I call this ground. So Vx is 280. At Y, it's going to be I delta minus I2 minus I1. Did I really call that I1? Because I did. Minus I1 minus 0.2 I delta, right? And I can solve for all of these in terms of node voltages. I actually know what I delta is already, so I don't have to think about that dependent source. So I delta is going to be Vx minus Vy over 2000. I2 is going to be Vy minus 0, because that's ground, over 2000. We're going to have I1 as Vy minus Va. This is what we want to solve for, right? Over 2000. And we have minus 0.2 I delta, which we already solved for earlier. Vx minus Vy over 2000, right? There's Y. And let's solve for node A now. Node A, we have 0.2 I delta coming in. We have I1 coming in. And we have I3 leaving. 0.2 I delta is 0.2 times Vx minus Vy over 2000. We have plus I1 coming in, which is Vy minus Va over 2000. And we have I3 leaving. So that's minus Va over 5600. Right? And now we can see we have two equations. We have two unknowns. We'd solve for it, and we'd find that Va is equal to 112 volts equals V Thevenin. So we have found our Thevenin voltage. Sweet. Let's move on. I Thevenin. And I think I'm going to copy my circuit here so we can actually see it. Well, I'm solving for I Thevenin. Okay, let's see if this works. Aha, it worked. It's a bit far down, but let's solve for I Thevenin. So I Thevenin, we're going to short the circuit, right? So we're going to say there's a short circuit coming over here. That shorts out this 5.6 kilo resistor. It's now gone. But we still want to solve for this. We still want to solve for this short circuit over here. I'm going to choose to use node voltage again because I prefer node voltage over mesh current. But you could solve using however way you wanted. There is X at X. Vx is still 280 volts. Writing our equation for node Y, we're going to have that I delta coming in minus I2 minus I1 1 minus 0.2 I delta, right? I delta is still Vx minus Vy over 2000. I2 is still Vy over 2000. I1 has changed, actually. So now, this is ground, right? VA is ground. So it's just going to be Vy over 2000. In reality, these three things are in parallel. But if you, it doesn't really matter if we're talking no voltage, but they are all in parallel. And then minus 0.2 I delta, and I delta is Vx minus Vy over 2000. And we don't need to solve for node A because node A is ground. So we have two equations. Well, sorry, we have one equation, we have one unknown. We'd solve for this. We'd get that Vy equals 80 volts, but we don't want Vy, we want this current over here. And so that current is I1. So I short circuit is equal to I1 plus 0.2 I delta from Kirchhoff's current law, right? When we do that, we're going to get that I1 is, we know it's Vy over 2000, and we know I delta is 0.2 times Vx, which is 280 minus 80 over 2000. When we solve that, we're going to get that I short circuit is 0.06 amps, and this is I Thevenin, right? So now we have solved for V Thevenin and I Thevenin. And we should be able to find R Thevenin from this, right? We know that R Thevenin equals V Thevenin over I Thevenin. V Thevenin we solved as 112 volts. And I Thevenin we solved as 0.06 amps just now. So we should find R Thevenin as 1866.67 ohms, right? Let's actually solve it in practice. And then we'll see if it matches. Okay. So let's get cracking, I guess. Let's paste this back in again so we can see our circuit. And remember, we have to deactivate all independent sources and then apply test voltage. So let's start deactivating sources. We only have one independent source in the network. That's this voltage source. It goes away, replaced with a wire. Right? We can't deactivate dependent sources. And then we need to add a test voltage here. V test. We want to solve for I test. Right. Once again, I'll turn to the power of node voltage because that's what I tend to use. So yeah, let's solve. So Vx at node X is grounded for this scenario. 0 volts, right? Vy, once again, same system equations. I delta, I'm not going to write this time. I delta is just, this is now 0 minus Vy over 2000. Go straight to the voltage step, since at this point we should kind of know it. Minus Vy over 2000, right? This is I2. And then the I1 is Vy minus VA. VA is V test. Let's call it V test. Over 2000. This is 0.2 times I delta, which we solved for the first expression. Right? There's Vy. This doesn't really help us much. We still don't know, what's happening. We want to solve for I test. And we want to get everything in terms of V test and I test and solve for the ratio. So I'm going to choose to use Kirchhoff's current law at node X anyway. So at node X, down here in ground, at node X, we're going to have that negative I delta plus I2 plus I3, and then minus I test. This is what I want you to introduce to the equation. And so when we solve it all out, this is 0 minus Vy, or 2000. This is Vy minus 0, 2000. This is V test minus 0 over 5600. And this is minus I test equals 0. And then we can solve for that. And now what we do? Let's simplify this Vy equation. When we simplify that, we're gonna get V test in terms of Vy. So we're gonna get that V test over 2.8 equals Vy. Let's substitute this into here. This equation is now going to only consist of V test and I test. So example 0 minus 0 Vy. This is negative V test over 2.8 times 2000 now, plus 2.8, no, plus V test over 2.8 times 2000. Plus V test, this is V test over 2.8 times 5600. Oh, it's me. Sorry, I missed negative. It should be negative here, making this positive. 5600 minus I test. That's going to equal 0. And then you just solve for V test over I test. And when you do that, you're going to get which equals 1866.67 ohms. So it matches with what we got earlier, all the way up there. And so then the Thevenin equivalent comes out to be 1866.67 ohms and 112 volts. And then we have A and B. So the whole circuit reduces down to this at those terminals A and B. All right, so I guess that's it then, right? That's the entire review. I covered everything that I think you guys said would be covered on your exam. These two, I guess, turned out to be a non-factor. So I guess we're done. So I'll wait a bit for the stream to catch up, and I'll ask if anyone has any specific questions, and I can answer them for a bit. But if not, then it's over. Wow. Is the stream really that far behind normally? Oh, I see. It seems my video... Has my video been frozen for this whole time? Wow, okay, my video is terrible. My internet must be going away. Okay, I've heard nothing. So I'm going to assume there are no questions. If there are, you can just ask the wonderful tutors over at the Discord. So good luck on the exam. And oh, the Wheatstone. Oh, I do see a question. The Wheatstone Bridge. Do you guys talk about the Wheatstone Bridge? I mean, it's a specific device just meant for like sensing voltages. I'm not sure what problems could be covered on it. Let me just Google the configuration real fast because I don't have it memorized. I'm pretty sure you should use Kirchhoff's current law for it. So you have some voltage source, right? You have a resistor, a resistor, a resistor, you have this. You want to know this resistor. You know this resistor. And this resistor you can adjust. And so basically you want to, and you have this, okay. You want to move this R2 so that zero current flows through here, right? And if the current is zero, that's our balance point. And if we're at the balance point, we can say that well, let's say there is zero, right? Then we can collapse this into like this. And we have R2, Rx, R1, R3, right? Then R2 over R1 is going to equal Rx over R3, right? Because the voltage, so the voltage across R1 equals the voltage across R3. The voltage across R2 equals the voltage across Rx. And so this ratio holds, and then you can simply just solve for Rx equals R2 over R1 times R3. And that's the whole point of some bridge. I don't really know what problems you would solve over it. This is how a Wheatstone bridge works, and this whole point is to sense currents going through it. As far as I don't have my textbook on me, so I can't just pull out Wheatstone bridge problems. But this is all I know about the Wheatstone bridge. So this is basically all I can show you. I can't think of anything else. I'm sorry. But if there's anything else I can see if I can help a bit with that. You could also derive the whole thing when it's not balanced, but I don't really think I want to do that.